conceptual model of a localizer system. This shows what result we're trying to get, but it won't be a practical system. Two VHF AM transmitters operating around 110 MHz are provided. One modulated with 150 Hz sinusoidal tone, the other with 90 Hz tone. Both transmitters use the same radio frequency source. This could be a low frequency crystal oscillator followed by frequency multiplying stages to reach the very high frequency used. By this means the transmitter outputs are locked together and can form a coherent transmission. The transmitters feed into two directional antenna systems mounted either side of the runway centerline. These might consist of several Yagi or log periodic antennas in a broadside array. In this instance, the antennas are physically offset so that the peak of the radiation pattern is to one side or the other of the runway centerline as shown. Because both transmitters are fed from the same drive source, the two radio beams form a coherent transmission, but with the modulation depth of the two tones varying depending on where the aircraft is in relation to the runway centerline. This is so-called space modulation of the transmission. The mod depth depends on where the receiver is in the space in front of the antenna system. When to the right of the centerline, the 150 Hz beam is stronger, whereas to the left it's the 90 Hz beam. Down the centerline, the two tones are equally strong, and this is the indication that the pilot uses for guidance to the runway. This simple system has a major flaw. If one of the transmitters has a higher power, or greater modulation depth than the other, as shown here, the line of equal modulation depth shifts away from the centerline. This could lead to an aircraft flying closer to obstructions, and also to not being adequately lined up when finally becoming visual with the runway. There is also a practical problem with adjusting and setting up the ILS. Changes to the course width, for example, require physical changes to the antenna system, in angle or phasing of the elements, both of which are not at all convenient. The system provides a steering signal called the course signal, which drives an indicator in the aircraft. The indicator is called the CDI, or course deviation indicator. Here's a runway with the ILS localizer at the left end. The course signal extends in a triangular shape as shown here, a few degrees wide. An aircraft outside or on the edge of the course receives a full-scale fly left signal as shown. When it is on course on the centerline, the CDI needle is centered and it moves over to the full fly right indication at the other edge of the course and beyond. The ILS course in effect funnels the aircraft towards the runway, with the course signal becoming narrower in actual width as the aircraft nears the runway, although the angular width remains the same. This ensures that the pilot is close to the runway centerline when eventually becoming visual with the runway lights, and he does not have to make large changes of course at low level close to the runway. In the real world, the CDI also has a horizontal needle which provides guidance in the vertical plane using the Glidescope transmission. This picture is of a CDI that shares the indications with a VOR, so that's why it's got a 0 to 360 degree scale on it. Modern aircraft use similar format displays but using computer graphics. The system in place in practical present-day ILS installations uses two signals, CSB and SBO, in a very elegant implementation of the required space modulation. CSB means carrier and sidebands. SBO means sidebands only. To understand how the variable modulation depth signal is formed, you need to understand three analog radio concepts. The first is the sum and difference technique. The second is the characteristics of double sideband suppressed carrier signals. And then some antenna theory, specifically what happens when you feed broadside antenna arrays in anti-phase. I'll deal with each of these concepts in turn. There'll be a minimum of maths and a maximum use of graphics, which I hope will make grasping the concepts easier. And the overall aim of this technique is to make a stable, reliable system where the course guidance is defined almost exclusively by the antenna system, which has a low dependency on the absolute output power of the ILS transmitter equipment. I should point out again that I'll be talking here only about the localizer aspect of the ILS. The Glidescope uses the same CSB and SBO technique, but with somewhat different antenna arrangements, but the object is similar, to form a stable, equal tone course signal with varying depth of tone either side of the correct glide slope. First, the sum and difference technique. This concept, by the way, is also used, for example, in analog stereo broadcasting on FM transmissions, which was also developed mid-20th century. Here we'll consider just the modulating tones on the two signals, 90 and 150 Hz sine wave tones. The CSB signal is modulated by the 90 and 150 Hz tones added together. The SBO signal is modulated by the 90 Hz tone added to the antiphase 150 Hz, that is, the 150 Hz signal is inverted or shifted in phase by 180 degrees. F1 and F2 represent the tones 90 and 150 Hz. They're actually the instantaneous value of the signals, for example voltage, but remember in practice they're varying sinusoidally with time. At some point in front of the ILS antenna system, the CSB signal has the value of M, F1 plus F2, where M is a factor depending on the transmitter power and antenna gain towards that point. Similarly, the SBO signal has a value of N, F1 minus F2, where N likewise depends on transmitter power and antenna gain towards that particular point. If we arrange to add and subtract the CSB and SBO signals, and we'll come to see later how this happens, we get the following effect. Taking the sum, we substitute the formulae, take away the brackets, collect the terms for F1 and F2. This term is bigger than this term, therefore F1 is greater than F2, and so the 90 Hz signal is stronger at that point in space. Similarly for the difference, the same process. Now this term is smaller than that one, so F1 is less than F2. F2 is greater than F1, so the 150 Hz signal is stronger at that point in space. This shows the center line of the localizer signal. Above the center line, the difference is taken between CSB and SBO to give a stronger 150 Hz signal. Below the center line, the sum is taken, causing the 90 Hz tone to predominate. Now we'll look at a block diagram of the ILS transmitter to see how these signals are produced. Two sine wave audio generators, one on 90 Hz and the other on 150 Hz, are provided. To give the CSB modulating signal, the two tones are simply added together. This could be as simple as a couple of resistors. The SBO signal also consists of the two tones being added together. However, in this case, one of them is inverted before being added to the other tone. In the diagram, I've shown the 150 Hz signal to be inverted. These are the two tones generated and added together for the CSB signal, and here's the antiphase 150 Hz signal added to the 90 Hz to provide the SBO modulating signal. The RF signals are generated as follows. There's a VHF carrier signal generator. This might be a low frequency crystal oscillator with frequency multiplying stages to reach the required frequency between 108 and 112 MHz. I've shown 109.1 MHz in the diagram. For the CSB signal, we need to produce a double sideband full carrier signal, that is, conventional AM signal. It can be done by using a balanced modulator to give a double sideband suppressed carrier signal, then adding the carrier back in at a suitable level to give the required modulation depth. The CSB signal passes through a linear RF amplifier which gives a few watts output to feed to the antenna system. The SBO signal is simply fed to another balanced modulator, and the resultant double sideband suppressed carrier DSB-SC signal is again amplified to provide the required few watts of power to the antenna system. In the SBO signal chain is a variable attenuator which controls the output power of the SBO component, and incidentally thereby adjusts the course width, which we'll look at later, and also to a variable phase shifter. This is nominally set to 90 degrees, but is variable over a small range to allow for tolerances between the CSB and SBO RF path to be compensated for due to differences in feeder lengths and so on. Another signal is added to the CSB transmission as shown here. A 1020 Hz sine wave generator is keyed with Morse code signals to form the ident signal for the ILS, so that the pilot can confirm that he's heading for the correct runway. There is also provision in the ILS spec for speech to be added to the transmission. This is rare to see in practice, although it could be used, for example, to give information to a pilot whose comm equipment had failed, or to give weather information. Here's a brief recording of an ILS transmission as received on a simple AM receiver. The low frequency tones, the 90 and 150 Hz, will probably only be audible if you're using headphones or a reasonably large loudspeaker. Now let's look at some characteristics of double sideband suppressed carrier signals. The SBO is this type of signal. First, a look at the spectrum of a conventional AM signal. There's the carrier in the centre and two sidebands, upper and lower, each side. If we take away the carrier, we're left with a double sideband suppressed carrier, or DSB-SC signal. This shows the waveform of an AM signal with carrier, a conventional AM signal. If you put this through an envelope detector, such as a simple diode, which in this case chops off the negative going parts of the waveform, and you filter the output, you recover the modulating signal. Now this is a DSB signal with the same modulating signal. I've shown the modulating signal as a blue line. If this waveform is put through a diode detector, you can see that the modulating waveform is not recovered. In fact, to receive this signal properly with a diode detector, you have to add the carrier signal back in the appropriate phase. Another interesting thing about the DSB-SC signal is that the carrier reverses phase as the modulating waveform passes through zero, as shown here. You can see the kinks in the carrier waveform at the zero crossing points. To show how this happens, the balance modulator in the transmitter can be considered to be an analog multiplier, with a carrier input, a modulating signal input, and the output, which is the product of the two. V out equals Vc times Vm. If we constrain Vm to be plus and minus 1, we can see if Vm is plus 1, the output is Vc. If Vm, the modulating signal, is minus 1, the output is minus Vc, which means that the carrier is inverted. If we look at this with some scope displays on the ports, Vm is plus 1, the output is the carrier in phase. Vm at minus 1, and the carrier phase is inverted. Now we can show what happens when Vm signal varies plus and minus. As it goes through zero, the carrier phase inverts. Let's look back at the DSB-SC signal again. We'll concentrate on just the area highlighted where the modulating signal falls through zero to a negative value. So here is the expanded view. For simplicity, I've shown the carrier as a triangular wave, but the principles apply equally to a sine wave. That's the DSB-SC signal with the modulating signal passing through zero. If we look at the red line, both the carrier and the DSB-SC signal are in phase, reaching a positive peak value at the same time. In the centre, the mod signal passes through zero, and now to the right of that point, if you look at the red line again, it shows that the carrier phase is opposite to that DSB-SC signal phase. Now if we add the carrier and DSB-SC signal together, which is what happens with the space modulation of the ILS signals in the far field, take the value of the carrier and of the DSB-SC signal at all points along the timeline to get this resultant signal. Now we can pass this signal through a diode or other envelope detector and filter the output to recover the modulating signal. You can see that it matches the modulating signal. It's falling from left to right. Now back to the same scenario, the carrier and the DSB-SC signal, and put on the red marker again. But now we'll shift the carrier phase by 180 degrees, that is, we'll invert it. Now you can see on the left, the trough of the carrier coincides with the peak of the DSB-SC signal. It's 180 degrees out of phase. To go through the same addition process as before, they get this waveform. Again, pass it through an envelope detector, smooth the output to get this recovered modulation envelope. You can see that this recovered envelope is inverted compared to that before. It's now rising instead of falling as we go from left to right. So the carrier in phase, carrier out of phase. You can see that the signal gets inverted depending on the phase of the carrier. To summarise, with double sideband suppressed carrier signals, inverting the phase of the added carrier inverts the recovered modulation phase when the resultant is rectified. We'll see later how this effect is used to form the space modulation required in the ILS transmission. Now to consider the techniques used in the ILS localizer antenna. First, let's look at a transmitter feeding into a single directional antenna like a Yagi or a log periodic. It might have a pattern like this. I should add at this point that all the antenna patterns here should be taken with a pinch of salt. They're only hand-drawn approximations of what exists in real life, just for illustration purposes. If we add another similar antenna and feed them both in phase, the pattern narrows and the maximum signal level increases. The gain goes up by 3 dB or so. But an interesting thing happens if we now add an extra half wavelength of feeder so that the two antennas are fed in antiphase. A sharp null appears on the center line. A receiver located on the center line picks up equal amplitude but opposite phase signals from each half, so the resultant cancels out to produce a deep null. In the ILS, this principle is used to define the runway centerline as shown here. The two antennas are fed in phase to produce a beam as shown in orange. This carries the CSB carrier and sideband signal. The SBO sidebands only signal is fed to the two antennas in antiphase, which gives a deep null on the centerline. It is this null which defines the course that the aircraft follows. I'll show how this happens in due course. Remember that both CSB and SBO are derived from the same carrier source, so they form a coherent signal with space modulation of the signal in the far field. And the requirement is to feed the CSB signal in phase and the SBO signal in antiphase to the two antenna elements. This can be done using a hybrid splitter. This is a useful component having 4 ports shown here. P1 and P2 are the two output ports which connect to the antennas. There's a summing port input and a difference port. Summing port, sigma input, and the difference port, the delta input. If RF power is fed into the summing port, sigma input, the signal is divided equally and half the power is passed to each P1 and P2 in phase. The difference port is effectively isolated and no power is fed out of this port. When RF power is fed into the difference or delta port, it's also split equally in power to the two output ports P1 and P2, but this time they are 180 degrees apart in phase. A possible implementation of this is the hybrid ring splitter, also called a rat race. This consists of a circle of feeder, for example coaxial cable, with an overall circumference of 1.5 wavelengths. The 4 ports are connected on the top half of the ring with quarter wavelength feeder sections between. The distance between the difference port and the P1 output port is 3/4 of a wavelength. If we now consider power fed into the summing port, sigma, it travels to P1 via quarter wavelength of feeder and also to P2 via the same length of feeder. The outputs are therefore in phase and split equally in power. Incidentally, if the power goes all the way around the ring, it still ends up at the output ports in phase. If we look at the path between the summing and different ports, the sigma and delta ports, there's a half a wavelength of feeder by this path and 1 wavelength by the other path. Signals therefore arrive at the delta difference port 180 degrees out of phase and thus cancel, so no power goes out of the delta port. The delta port is in effect isolated. Power fed into the difference port, delta, goes via 3/4 of a wavelength feeder to output P1 and a quarter wavelength feeder to P2. These outputs are therefore 180 degrees out of phase. The same consideration applies to the path between the difference of the summing inputs. The signals cancel out. Thus we have the requirements to feed the CSB and SBO signals to the antenna array. The CSB signals fed in phase to the antenna, the SBO signals are fed out of phase. But now we need to look at the phase relationship between the signals in the main beam, the CSB, and the two lobes of the SBO signal. We'll do this by considering some vectors. This is a plan view. The two antennas are represented as point sources, equally spaced either side of the center line. With both A and B in phase, at the receiving point R, somewhere on the center line, equal signals are received from both antennas and the vectors add to produce 2 times VA resultant. With both A and B in antiphase, the two vectors oppose each other and so no resultant signal appears. There's a null on the center line. Now consider a location R displaced above the center line. Now there's a path length difference between each antenna and the receiving point. It's shown here as alpha degrees phase lag from the B antenna. Showing this as vectors, VA is here, and the vectors are assumed to rotate anti-clockwise, by the way. VB lags by alpha degrees. We get the resultant signal by vector addition as shown. The sum signal lags by alpha over 2 at this particular displacement from the center line. If we now drive A and B in antiphase, vector VB is shifted 180 degrees as shown. The resultant signal is shown here. We now need to consider the phase angle between the in-phase resultant and the out-of-phase resultant signals. Angle beta is the base angle of this isosceles triangle. It's given by 180 minus alpha all over 2 or 90 minus alpha over 2 degrees. This angle is also beta, so we can work out the phase angle between VR and VR dash, which is beta plus alpha over 2, or 90 minus alpha over 2 plus alpha over 2, which results in 90 degrees. Now we consider a point R displaced equally on the opposite side of the centerline. Now it's VA which has the extra path length alpha. With A and B in phase, the resultant is the same alpha over 2 lagging vector as appeared before. However, the resultant for the outer phase condition is now in this quadrant, and it's 180 degrees different from that when the point R was above the centerline. To summarise, at a particular displacement either side of the centerline, the summed in-phase signal VR is always alpha over 2 degrees lagging, whereas the outer phase signals are always 180 degrees apart and plus or minus 90 degrees from the in-phase signal. You could also say that one of the lobes is 90 degrees and the other is 270 degrees from the in-phase signal. So now you can see perhaps why the SBO signal has to have that extra 90 degrees phase delay added in the transmitter, so the CSB and SBO signals are either in phase or 180 degrees out of phase, depending on which side of the centerline you're on. Let's now look at practical localizer antennas. I've shown here 6 directional antennas. They could be Yagis or more commonly these days log periodic antennas. The blue blocks represents the power distribution feeders, which give the required power distribution and phasing to form a narrow radiation pattern. A mirror image of the antenna system is placed symmetrically about the centerline as shown. This picture is an 8-element log periodic array at Coventry Airport, just about the smallest practical array that's used these days. At the other end of Coventry's runway is this 14-element array of log periodics. Two halves are fed in phase with a CSB signal to form this beam a few degrees wide across the centerline. The two halves are fed out of phase with the SBO signal to produce this sort of pattern with a deep null along the centerline. As we've already seen, a hybrid splitter can be used to feed the two halves with appropriately phased signals from the CSB and SBO transmitter outputs. The relative phase between the CSB and SBO signals is shown here. The two lobes of the SBO signal have a 180 degree difference in phase. The carrier in the CSB signal has a 0 or 180 degree phase difference to the SBO signal, depending on which lobe, above or below the centerline, is considered. This phase difference, by the way, is 90 degrees due to the antenna characteristics we talked about before, and 90 degrees due to the phase shift added to the SBO signal in the transmitter. On the centerline, the deep null in the SBO pattern means that only the CSB signal is received with its equal 90 and 150 Hz tones. This defines the center of the course towards the runway that the aircraft uses for guidance. The sum and difference technique works so that the CSB and SBO signal are summed in space to the left, or below in this case the centerline, and the difference is taken to the right of the centerline. Hence the 90 Hz signal is strung below the centerline here, and above it, where the difference signal is taken, the 150 Hz signal predominates. Now note that if the CSB signal reduces in amplitude as shown here, it doesn't affect the centerline of the course signal. That is solely defined by the deep null in the SBO antenna. This antenna characteristic can be made very stable, making for a reliable and safe long-term approach guidance system. Now, in practical antenna implementations like this, there are inevitably low-level spurious side lobes to the radiation pattern, shown schematically here. They're typically more than 15 dBs down on the main signal. However, there is the possibility of a false course being picked up by an aircraft as shown here, especially if the side lobe is mainly of the CSB signal with its equal 90 and 150 Hz tone modulation. To prevent this false course happening, an extra 2 signals are radiated using 2 or 3 of the localizer antennas either side of the centerline. These give a broad CSB and SBO pattern with a radiated power about 10 dBs below that of the main course signal. By this means the spurious signals from the side lobes are overpowered with our full-scale CDI signal, fly left or fly right, as appropriate. This extra transmission is called the clearance signal, as opposed to the main course signal, as shown. Now, some localizers use a separate radio frequency for the clearance signal. This is often beneficial as the beam forming necessary can be done more easily for the two signals if they are on different frequencies. This especially applies where the ILS is used for category 2 or 3 systems, where the greatest precision is required to safely guide aircraft to land. Here I've shown the course signal on F1 and the clearance signal on F2. F1 and F2 are typically separated by about 8 kHz, so they still fall within the fairly wide nav receiver passband. Fairly obviously, these systems are called two-frequency localizers. The clearance frequency is fed to the inner 2 or 3 antenna elements on each side, as shown here in light blue. There's also a possibility of using a completely different antenna array for the clearance signal as shown. This is possible because radio coherence isn't required, as either the strong coarse signal or the weaker clearance signal capture the receiver detector at any one time. Coherence is required, however, in the modulation frequencies, so the 90 and 150 Hz tones come from the same sources for both coarse and clearance transmitters. If we now look at a nav receiver IF passband, it's quite wide at about 30 kHz. A leftover from earlier times when VHF receivers and transmitters were a lot less stable than they are today. On a single frequency localizer, the ILS signal sits in the centre of the passband as shown. For a two-frequency localizer, each frequency is offset about 4 kHz from the nominal centre frequency, so they end up about 8 kHz apart. When the aircraft is on course, the coarse signal is stronger and captures the receiver detector and so drives the CDI indication, because the clearance signal is about 10 dB down. However, the situation is reversed when the aircraft is in the clearance area. Coarse signal is weaker and the receiver AGC brings up the clearance signal to full level in the IF, so it captures the detector and drives the CDI. Now we look at course width, what it means and how it's adjusted. This shows an aircraft flying towards the ILS localizer. Initially the aircraft is around 40 degrees off the centre line. The localizer signal may be unusable, so the CDI flag is showing. As the aircraft reaches 35 degrees off centre or so, the ident signal becomes audible and the CDI flag clears and the needle shows a full-scale fly right. This is maintained until about 5 degrees off centre, when the CDI needle comes off the end stop and starts moving across to the left, passing to the centre when the aircraft is on the centre line. If it continues through the centre line, the CDI shows increasingly fly left, reaching full-scale deflection at about plus 5 degrees in this case. The full-scale signal is again given until the aircraft reaches plus 35 degrees, when the flag shows and the ident signal becomes inaudible. If we show the CDI position graphically, it has a sector of full-scale fly right, a nominally linear region in the centre as the CDI pointer moves across the scale, then full-scale fly left. These are the clearance and course signals as shown. The course width is shown. It's the width of the linear region. And this is a graph for a narrower course width. Now look at a runway with the localizer located on the left. The course signal is shown here as a narrow fan triangular shape. Note this does not represent in any way the beam shape of the radio waves involved. It merely shows where the CDI gives course steering information to the pilot. The CDI gives full-scale indications when the aircraft is on the edge of the fan shape as shown here. And the course width is defined as the width of the course signal at the runway threshold, and ICAO requirements state it should be 210 metres or so. This means that the signal needs to be a narrower angle for longer runways. The course width is set as follows. Let's look back at the transmitter block diagram. I showed a variable attenuator in the SBO signal chain which sets the SBO output level fed to the antenna system. This sets the course width as follows. Looking back at the sum and difference technique, the SBO signal modulation component in the file field is given by N F1-F2, where F1 and F2 are the 90 and 150 Hz tone levels, respectively. The factor N depends on transmitter power and antenna gain towards that point. If we make N, say, bigger, as shown here, by increasing the SBO transmitter power, you can see that this term F1 gets bigger and the F2 term gets smaller, meaning that the difference in mod depth is greater, and so the CDI indication is more sensitive and reaches full-scale deflection sooner. That means that the course width is less. Let's show this graphically. We vary the SBO signal power, as shown by the blue patterns here. As the SBO signal increases, the course width reduces, and it's relatively easy to set the required course width in this way. There's one major drawback in the CSB-SBO scheme of things. Here's an aircraft flying towards the ILS with the CDI providing steering information. Unfortunately, the SBO signal fails, or is turned off for some reason. Immediately, the CDI centres as the receiver is getting the CSB signal only with its equal tone modulation. This is a highly dangerous situation, as no matter where the aircraft is in relation to the centre line, it receives an on-course signal. For this reason, great care must be taken to prevent pilots using the ILS if the SBO signal is absent for any reason. Equipment failure is taken care of by comprehensive monitoring and automatic changeover to standby equipment. But sometimes during maintenance it's necessary to radiate just CSB signals alone. Appropriate warning to the pilots must be given in this case.